G'day everybody. In this lesson we're going to begin covering the normal distribution for probability. I'm going to cover this topic in 3 lessons. This is part 1. In this lesson we're going to talk about how we define a normally distributed variable. We'll do a lot of sketching of functions that are normally distributed, and we're going to use our CAS calculator to calculate probabilities with the normal distribution. I'm going to start by talking about a particular variable, the speed of a fast bowler, and we're going to assume that this is an example of a normal distribution. Bowlers don't bowl at the same speed with every single delivery. There would be some sort of average, and we refer to this as the mean. And we can see we've used this symbol before for the mean, the Greek letter mu. There would be some measure of variation. Sometimes the bowler would bowl slightly quicker or slightly slower than the mean speed. And so we have 2 measures of variation. We could use the variance, or taking the square root of that, we could use the standard deviation. And we are assuming that the speed is a continuous random variable. It's not discrete like other variables we've seen in the past. Before we look at how we define a normal distribution or a normal variable, let's recall how we used mathematical notation to define a binomial distribution. So we used some sort of code to say that it was binomial, BI, and we identified 2 parameters that define that function. Once we know those things, we know everything we need to know to solve problems with this binomial distribution. It was the number of trials, or the number of Bernoulli trials, and the value of P, which is the probability of success of one trial. And so once we knew those 2 things, we could solve problems. And the discrete distribution was represented as a table, where the top row, x, was all the possible values that that variable could take, and all of their respective probabilities in the bottom row of the table. In a similar way, we define a normal distribution. So once we know 2 things about the normal distribution, we can start solving problems. So we use capital N as code for a normally distributed variable, and all we need to know is the mean and the variance or the standard deviation. Just pay attention to the fact that when we define a normally distributed variable, we do use the variance. However, we hardly ever use the variance when we're calculating probabilities or solving problems. We always use the standard deviation. Because it's a continuously distributed variable, we don't have a table to represent the distribution, but we do have a graph. And you've seen this sort of graph before. It's what we commonly refer to as the bell curve. And the bell curve is along a horizontal axis, and in the middle of that axis is the mean of the distribution. The bell curve is an example of a probability density function, and so the properties that we've studied before with probability density functions are the same properties that this curve has. It's always important to remember that along the horizontal axis, the bell curve has an asymptote with the x-axis, and so it's a continuously distributed variable from negative infinity to positive infinity. And because it's a probability density function, the area underneath the bell curve is exactly 1, from negative infinity to positive infinity. So how do we sketch a normal distribution? First of all, sketching these graphs is key to understanding the distributions and solving problems. I highly encourage all students to always sketch a normal distribution when you are thinking about a question and trying to solve a problem. With a bit of practice, doing a sketch is something that can be done very quickly. Let's take our fast bowler, and let's say it's defined by this distribution where the mean is 150, the variance is 4. So what do we now know about this function? We've got a mean which is 150 kilometers per hour, a variance which is 4, and a standard deviation which is the square root, which is 2 kilometers per hour. When we use the mean and the standard deviation, that's basically all we need to sketch the curve for this distribution. And this is what it will look like. So we start off by drawing a bell curve along an x-axis. Down the middle, we plot the mean of the distribution, so there's our 150 kilometers per hour, and the standard deviation, we can usually fit, or we can always fit, 3 standard deviations practically to the end of the bell. So if our standard deviation is 2, you can see I've gone from 100, 152, 154, 156, and 3 standard deviations in the negative direction, which takes us down to 144. It's worth mentioning now that our mean, which is in the middle, for a symmetrical distribution like the normal curve, that means our mode is also 150 kilometers per hour, and our median is also 150 kilometers per hour. So that's one property of the normal distribution. Its mean, mode, and median are all exactly the same value. I say practically all deliveries will be in that range of 144 to 156. That's something that all normal distributions have in common. 3 standard deviations either side of the mean. Just got a little typo there, I'm going to fix that up. Minus 3 standard deviations, positive 3 standard deviations. There is a small minimal chance that a delivery could be lower than 144 or higher than 156, but that probability is extremely low. So let's use this distribution to calculate an example. Let's look at the example. What is the probability that the next delivery from our bowler will be somewhere between 151 and 154 kilometers per hour? Here's our normal distribution, the sketch that we've just seen, and I've shaded in the area that we're talking about. So there's 150, 151, up to 154. So the probability that we are calculating is equivalent to the area that we have shaded in this probability density function. And this is where we use the CAS calculator. So we go to our probability menu and we select the distributions, and the second function in that submenu is the normal CDF function. It'll open up a pop-up window with a lower bound, an upper bound, a mean and a standard deviation. These 3 values here are default values, and in our third lesson of this topic we'll find out why those particular values are there. But for this problem we're interested in the area from 151 to 154, so they're the lower and upper bounds. Our mean is 150, and our standard deviation, not the variance, the standard deviation is 2. And when we click OK, it takes us back to the calculator page, and we can see our probability as the output. So that's the normal CDF function, which you'll use quite a lot for this topic. So there's our probability. Our area was approximately 0.286 or 28.6%. That's the probability that the next delivery from our bowler will be between 151 and 154. Here's a different question about the same distribution. What's the probability that our next delivery will be slower than 147? You can see here our same distribution, but now I've shaded in an area that is below 147 kilometers per hour on the horizontal axis. Going back to our normal CDF function, we're going to use negative infinity as our lower bound. Our upper bound is 147, and our mean and our standard deviation are the same as before. And we can see our output now. It's something like the area that we saw, so we saw a small area in our sketch. That probability that x is slower than 147 kilometers per hour is 6.7%, or 0.067. One more question with this distribution. What's the probability that the next delivery will be more than 2 standard deviations above the mean? So we're looking at the probability that x is greater than the mean plus 2 standard deviations. We'll do that calculation with a mean of 150 and a standard deviation of 2. That means we're interested in the probability that the next delivery will be greater than 154 kilometers per hour. Once again, using our normal CDF function in the probability menu, this time our lower bound is 154 and our upper bound is infinity. So on the calculator, when we want to type in infinity, this button down here in the bottom left of the calculator where the pi symbol is, we click that and we can find our symbol for infinity. And we can put that in as the upper boundary. If we had forgotten where that button was and we couldn't remember where to find that probability symbol, actually typing any really extremely large number would be fine. So if I'd type something in there like 100,000 kilometers per hour, I would get the same result practically. We're still using the same mean, standard deviation, and there's our output. So the probability that the next delivery will be more than 2 standard deviations above the mean is 0.023. So that concludes the first part for this topic. We've talked about how we define a normally distributed variable. We've seen how we use the mean and the standard deviation to create a sketch of a particular distribution. And then once again, always make a sketch when you're thinking about or answering a question to do with a normal variable. And in this lesson, we've used our normal CDF function on the CAS calculator to calculate some probabilities. Please write down any questions that you have. Complete the Google form that goes with this lesson to log your attendance and to check your understanding. Thanks very much.